Hello everyone, welcome to the class of physics by CDR, and this is another lecture for the chapter semiconductor and device. And in this lecture I will discuss about Zener diode. So let's start. It is specially designed to operate in reverse breakdown region. It is actually highly doped and defect free PN junction diode. So we can operate it in the breakdown region again and again, and its power dissipation capabilities also high, so we can operate it at very high reverse current. Let's see the circuit symbol of Zener diode. This is the circuit symbol of a Zener diode. I will show you the reverse characteristic of a Zener diode, and let's see the circuit diagram of a reverse characteristic of a Zener diode. Here we are not interested with the forward characteristic of the Zener diode because we use Zener diode for voltage regulation, and Zener diode behave as a voltage regulator in reverse bias condition. So we are interested with the reverse characteristic. Okay, and the circuit consists of a voltage source, and this is the source resistance, and it is used to protect the circuit, and this is milliammeter, and it is used to measure the reverse current flowing through the Zener diode. This is the Zener diode, and here a voltmeter is connected to measure the voltage across the Zener diode. Okay, now actually here the source is connected in such a way that the Zener diode become reverse bias, and we know for reverse biasing of the PN junction diode, positive terminal of the source is connected to the N side and negative terminal of the source is connected to the P side. So the Zener diode is reverse bias. Now if we increasing the reverse bias voltage, actually this is variable source. If we increase the reverse bias voltage across the Zener diode, initially the current almost constant, does not depend on the reverse voltage, and the reverse voltage is small, and after certain value current increase suddenly, and the voltage for which current increase suddenly, this voltage is called breakdown voltage, and the phenomenon is called Zener breakdown. Okay, there are two mechanisms for the Zener breakdown. One is Zener breakdown, and another one is avalanche breakdown. Now we are going to discuss about Zener breakdown. For Zener breakdown, doping concentration of a PN junction diode is very high, and so the depletion region, actually this is the PN junction diode, and in a PN junction diode there is a depletion region formed at the junction, and this is the depletion region, and we already have discussed in previous class about PN junction diode. So this is the depletion region. When the doping concentration is very high, then the depletion region become very thin. And you know, these are the neutral portion of the PN junction diode, and in the neutral portion there is huge number of free carriers. So these two sides behave as a conductor, and when a potential difference is given to the PN junction diode, completely drop at the depletion region. So when the doping concentration is very high, the depletion region become very thin, and we know the electric field E equal to minus dV dx, and since depletion region is very thin, so here dx is very small. So very small reverse bias voltage applying across the junction produce very strong electric field at the junction, and this strong electric field directly break the covalent bond at the junction and produce huge number of minority carriers, so current increases abruptly. So this is the mechanism of the Zener breakdown, and Zener breakdown occur around 6 volt. Now I will study the Zener breakdown with temperature. What will happen? We know temperature also helps to escape the electron from the covalent bond at the junction. So with increasing temperature helps the electron to escape from the covalent bond. So with increasing temperature, the lower field is required to break the covalent bond at the junction. So with increasing temperature, Zener breakdown voltage will be decreases. That means the temperature coefficient of Zener breakdown is negative. Now we are going to discuss about avalanche breakdown. In case of avalanche breakdown, the doping concentration of a PN junction diode is comparatively low. Actually, doping concentration is not low, but with respect to the Zener diode, the doping concentration is low. And for low doping concentration, the depletion region become widened. So small reverse bias voltage does not produce very strong electric field that directly rupture the covalent bond at the junction. But here the minority carriers, this is the p side, and here the minority carriers are electron, and electron flows down the junction. And when the electron cross the junction, they acquire energy from the electric field set up at the junction, and when they acquire sufficient of energy from the electric field and strike the immobile atom at the junction, electron hole pair is generated, and newly generated carriers also acquire energy from that electric field and again collide with the immobile impurity, and in the same way again produce electron hole pairs, and the process is cumulative. So with very small time, huge number of carrier is developed, and so current increase abruptly. So this type of breakdown is called avalanche breakdown. And actually here breakdown occurs due to the collision of electrons with immobile impurity atom at the junction. So with increasing temperature, the collision probability of electron increases. So what will happen? We know, let's say the first collision of electron takes place at that position, and the second collision takes place at that position. When electron collide with electron and also with the impurity atom, the energy of the electron become 0, and again at the second collision energy become 0. Actually electron acquire energy from the electric field in the space between two successive collisions when they are moving freely. Okay, but with increasing temperature, the collision frequency increases. That means the electrons collide very fast. So second collision takes place before that position. That means the distance between two successive collisions become reduced. So to acquire sufficient amount of energy in less space, high electric field is required. That means high reverse bias voltage must be applied across the PN junction diode. That means with increasing temperature, the avalanche breakdown voltage also increases. So, the temperature coefficient of avalanche breakdown voltage is positive. And for avalanche breakdown occur at very higher voltage than the Zener breakdown. Okay. Now I will discuss about the voltage regulation of a Zener diode in the next class. Thank you.